Okay, the chain rule. So this concept from Calc 1 gets applied here when we get into partial derivatives now. So these first two examples, you can read that, but pretty much we're finding dw dt as a function of t, and we're just going to use the chain rule. And we evaluate a specific value t. The value of t sometimes does not matter though, if like the derivative is pretty much stuck at a certain value. We'll see. In this first one, it's actually pretty easy because of the so you have x squared plus y squared as our function w. X equals cosine t, y equals sine t, and t equals pi is what we have to evaluate it at the end. So dw dt is equal to dw dx times dx dt plus dw dy dt. So dw dx is 2x and dw dy is just 2y. It's a very simple function. As its derivatives go like that. And this one, oh yeah, dx dt is negative sine t and dy dt is cosine t. So first we plug in these values, you get 2x negative sine t plus 2y times cosine t, so it's negative 2x sine t plus 2y cosine t. Then we have to plug in x and y so we get it all in terms of t. That's what we want. So x equals cosine t, so you have so you're negative 2 cosine t sine t plus 2 sine t cosine t. And look, they cancel out to 0. So it's just 0. And then b is easy because it's just dw dt at t equals pi is equal to 0. Because anything, it's going to be like that for any value you plug in, any value that can exist. Okay, here's a little bit off. We have these. There's going to be some really long ones though. Like this one, the next one are more nuanced and harder. Especially the next one. I've tried to limit the examples, but we should show enough examples as well. So w equals x divided by z plus y divided by z. X equals cosine squared t, y equals sine squared t, z equals 1 divided by t, t equals 3 is what we're going to evaluate it at then. So the chain rule becomes this mess: dw dx dt x dt plus dw dy dt plus dw dz dt. The only thing is that it's not the hardest formula to remember. You just keep on adding more and more, like for 2 or 3 variables, just add on those things. In general, I think the way to remember it is, in the end, you want everything to be in terms of, like, in this case, like dw dt, you want to go from your intermediate, like x, y, and z are kind of like intermediate variables, what it says in the book, if you really look at it. You basically are always going to have dw dt when you're looking for it as the two things like that. So in a way, I know it's not technical, but dx and dx cancel out here, dy cancel out, and dz dt cancel out. I think that's just the best way to think of it. So in the end, you just have different parts of dw dt to different x, y, and z components almost. But I don't think, it's not really technical to say that, but I think it's one way of thinking of it. Whatever way works best for thinking of it. But that's why we have to take 6 derivatives and then 3 partials and 3 normal derivatives. So dw dx and dw dy, those are easy because it's just 1 over z for both of them in the end. Because it's basically x times 1 over z plus y times 1 over z. So with x, it's just 1 over z. Y, it's the same thing. dw dz, a little bit harder, but it's basically like you make it a negative power and you take down the power. You use the power rule. And you do it for both the x over z and y over z, basically. So negative x plus y over z squared. And of course it's power rule for that, cosine squared t sine squared t. And even this one. I think the work's pretty self-explanatory. And so I plug in these values. I kind of skipped ahead. Like, this is kind of skipping a little, kind of cheesing. I saw, no matter what, this is 2 sine t cosine t and negative 2 sine t cosine t divided by z each. So they're going to cancel each other out, pretty much is what I saw. Basically, these are going to cancel each other out. Technically, I should plug in x. I should wait and plug in x, y, and z. You know, I should do that. But this won't change because it's going to be basically divided by z. Something plus something equals 0, and 0 divided by anything is going to be 0. So I just canceled them out. And that's why, because it's a negative, and it's a positive version, negative version of the same thing. So all we have is negative x, the fraction x plus y. I mean, yeah, it's negative x plus y divided by z squared times negative 1 over t squared. I made this a little bit more complicated. But you plug in x, y, and z, you get cosine squared t plus sine squared t. You know, it's all negative fraction divided by 1 over t squared times negative 1 over t squared. And this becomes 1 because cosine squared plus sine squared is going to be 1. So basically it's negative t squared times negative 1 over t squared is equal to 1. And it becomes negative 1 times negative 1, which is equal to 1 basically. So, and then at the point t equals 3, it's going to be 1 as well. Okay, now it's time for the messy one. If you can do this, I think you have a good understanding of this. So basically we have to do two parts of this. We have to find dz du and dz dv, and this is very much a lot of stuff going on. Everything's on here, okay. Just follow it. Basically it's like in this case, when you have a problem like this, it's going to be dz du and dz dv. dz du is dz dx dx du plus dz dy dy du. It's a very similar format to one, but these are all partials this time. Everything's a partial derivative. But it's a very similar format. You have all these complicated functions like x equals ln u cosine v and y equals u sine v. I think just read over this slowly and carefully and see it at your own pace. Eventually you get this at the end, 2 square root of 2, ln square root of 2 plus 2 square root of 2, and you could simplify that further, and I think in the next one I do kind of simplify it more. But that's at the point, and then you get at a certain point. It just takes some effort to make sure you understand when you're taking derivatives and all that. Here's the next part, was dz dv equals dz dx times dx dv plus dz dy. Good thing you already have dz dy and dz dx from this part, at least that saves you a little step. You just have to figure out, you do dx dv and dy dv. It's just as complicated as before. And you get the final answer when you evaluate at a certain point, at the point given. But I can't really, it's really just following what I'm doing. And like a dumb person, I basically, I made this negative tangent v. You're gonna have to convert that back, but whatever. Just remember, sine divided by cosine of something is tangent of that. That's all I did, was I converted, that was unnecessary because you're going to have to right away do some cancellation and all that. As you'll see down here, I eventually had to change back. But just at your own peril, you can try these problems and make sure you see how I do them. But okay, implicit differentiation. So dy dx equals negative fx over fy is the most simple form of it. Here's an example. So you have fx equals, you want to evaluate at a certain point. X cubed minus 2y squared plus xy equals 0. So just 3x squared plus y is obviously the derivative was x. And y is 1 if y is negative 4y plus x. And then I distributed the negative sign to get it. It's nice, so it's negative x, 3x squared plus y divided by negative x plus 4y. And at 1, 1, you just plug in the 1 and 1, like x equals 1 and y equals 1. You get 4/3. I don't think there's a lot to explain with these. You're just doing mostly derivatives and everything. Same, you have this function. You want to find, okay, so this is where you do it. So dz dx is negative fx divided by fc, and dz dy is negative fy divided by fc. And it's the same process as before, basically. You want to evaluate at 1, 1, 1. Find fx, fy, fz, and then do the proper divisions to get your results. I distribute the negatives out each time just to get them outside of the front. I don't think you really have to do that, but it's one way of doing it. Okay, final part is finding specific signs, and again, so in this case, you have to do dWdr, and this time we have all 3 parts of it. You can read it at your own, try to make it very clear. At least these derivatives aren't extremely hard to do, but it's the fact that we wait to plug them in at the end. Very technical. It does all simplify though in the end when you have the values. This mess of whatever it is. Before you plug in all the r equals 1 and s equals negative 1. And you finally get 12 for this. And same thing with this one. This one's actually a pretty simple one overall. I overcomplicated at one point, but that's a waste. It's quite literally like dz du is just dz dx dx du, and dz dv is dz dx dx dv. Really, just the more simpler one. Except we have to make sure you simplify, like ln2 and v equals. You just have functions z and x basically in this problem though. With u and v being given specific value. But in the end you get 2 and 1 as shown here. For dz du is equal to 2 at those when u equals ln2 and v equals 1, and dz dv will be 1 when u equals ln2 and v equals 1. But there's not much to say really commentary wise on all this. Is just reading what I've done and make it as clear as possible.